Let us see now some useful terms and splitting of the signal. Okay, spin-spin coupling. One nuclear spin, that is one rotating proton, influences the spin of the other nucleus, the adjacent proton. The splitting is effect on NMR signal caused by spin-spin coupling. And what is coupling constant? J. It is the spacing between lines in the splitting pattern. Now, these rules and restrictions of the splitting signal will help you to interpret the NMR signal. The general rule, the basic rule, the signal for a proton with n neighbors is split into n plus 1 lines. We have seen this rule before also. So, rules and restrictions for proton, spin coupling. First, only non-equivalent protons can couple. If you'll observe this example, we have HA, HB, HC, HD. Okay. Now, the last is HA only. Okay. Now, if we consider this, HB, that is HB over here, can couple with HC. HB and HA will not couple. These two will not couple because they are equivalent. HC and HD do not couple because they are equivalent. HC cannot couple with HD because if you observe closely, they are absolutely equivalent. There is only one coupling possible. Now, second, protons separated by more than 3 single bonds usually do not couple. Okay, so HA can couple with HB. This coupling is possible. Okay, HA couples with HC. So 1 bond, 2 bond, 3 bond. This is also possible. But HA cannot couple with HD because it will be separated by 1, 2, 3, 4. 4 bonds. That's why this coupling is not possible. This coupling is not possible. Pi bonds do not count towards this bond limit, but J may be too small to observe. See, pi bond is in fact is the bond which reduces the bond length. So this particular rule will stand even if there is a pi bond. But only thing is it will reduce the J value. Okay, it will reduce the G value. So HA here and HB over here will couple. It is possible. HA here and HC here. So 1 bond, 2nd bond and 3rd bond. So it can also couple. Okay. Then HA couples with HD, but J may be small. So this is 1 bond, 2 bond, 3 bond and 4 bond. You must have seen that here it was said that if there are more than 3 single bond, the word single is important. Okay. If there are more than 3 single bonds, it will not couple. But if it is a pi bond, it can be considered as free spacer. You may not count it. So it will be 1, 2, 3. So yes, this coupling can also occur, but J value will be very small. So next rule, protons separated by more than 3 single bonds usually do not couple. Now we are going to see in case of aromatic compounds. See, benzene ring as a whole can be seen as one big spacer. I hope you get it what I am trying to say. If pi bond is spacer and we cannot count it, benzene ring there is always delocalization of electrons. So although we see that these 3 pi bonds are distinctly shown, in fact you must have seen this in your resonance theory, they all are delocalized. So the entire benzene ring can act as a one big spacer. Okay, so if I want to see the distance between HD and HC, it is for 1, 2 bonds. So they are as good as attached to the same carbon only, like in case of geminal coupling. But let us see. I hope you understand the scenario, what it is, why that one big spacer is benzene ring. So all benzene ring protons may couple with each other, but J value is too small. HA, HB, HC and HD all couple with each other. Now J between AD will be very small to observe. So it is as good as one big signal. Benzene ring blocks some coupling that we may expect to observe. Let us see one example. Observe the diagram, observe the structure. One may expect that since we are not counting this bond because it is a pi bond, so the hydrogen separated over here is say bond number 1, bond number 2, and third bond is between carbon and hydrogen. This is bond number 3. Okay, so this hydrogen and this hydrogen should couple, but it is observed that this coupling is blocked. Okay, even this coupling is also blocked between CH3 and CH2. Now, why this is important is we have said that the benzene ring is like one big pi bond only, okay, and it is acting as a free spacer, one big free spacer. But this is true for hydrogens that are directly attached to benzene ring, but not for hydrogen those who are present on the functional group attached to the benzene ring. I hope you understood the difference between these two. Now, next, observe the diagram in front of you, observe the structure in front of you, and just predict how many signals you will get and how will be the splitting in that signal. So, as per the rules that we have studied, this NH2 should give you triplet because N neighboring, there are two hydrogens which are neighboring. So 2 plus 1, you should get a triplet. For this CH2 in the pink, you should expect to have, say, 2 hydrogens on nitrogen, 2 hydrogens on the carbon. So 4 plus 1, a pentate. For this CH2 also, we should expect 2 plus 1, 3, so 3 plus 1, a quartet. And for this hydroxyl, one may expect a triplet, that is 2 plus 1. So here we are following n plus 1 rule, and this is what should we get. So this is the general expectation. Are you with me, students? Are you getting it?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this is what we expect. Okay, this is what we expect. But in reality, this is not observed. These heteroatoms that are present, atoms other than carbon, they are way more electronegative than carbon. Because they are electronegative, they are pulling the electrons from these hydrogens very strongly. The electrons are pulled very strongly, and that's why coupling pattern usually differs for them. So what happens is this hydroxyl group, instead of giving you a triplet, will give you singlet, and same with this NH2. This NH2 will also not give you triplet, it will give you a singlet, a single peak. And the reason behind it is the electronegativity of the nitrogen. Now, because of this strong electronegativity, as if there is some kind of force that is separated this hydrogen from rest of the molecule, separating this hydrogen from rest of the molecule. So when you want to predict splitting of this set of protons, you need to consider only these protons. So adjacent protons are 2, so 2 plus 1, a triplet is observed, and even for this set of proton, triplet is observed for 2 plus 1. Now, one small question. These two triplets will overlap each other or they will be completely different? What do you guess? Very good, Aarti. They will be completely different. Saili, Aarti, very good. Shakil, Pooja, Priyanka, Sandhya, Vishal, very good. So they will be totally different. The reason being, the electronegativity of nitrogen is completely different than that of the hydroxyl group. So these two set of protons are completely different environment. So splitting of hydroxyl and splitting of NH protons may be observed in very rare circumstances. Now let's talk about, अच्छा हमने ये already discuss किया है. Let's move forward to FT-NMR. Okay, FT-IR we have studied that how all the electromagnetic radiation of different frequencies simultaneously bombarded, and it gives you a little bit complicated pattern of the electromagnetic radiation which consists of all the wavelengths, that is called as you can say mm, the combination of all the frequencies, all the wavelengths. Okay, and if to that pattern, you must be remembering that decay signal. Okay, if you apply the mathematical operation of Fourier transform to it, we can change this into a more meaningful manner. This is with respect to time scale. This is with time scale, and this is, you can call it as per wavelength, as per wave number, or in case of NMR, you can count it as a frequency, or even in case of NMR, we can convert it to ppm. So there will be formulas for that. We don't want to go in mathematics of it, but we can simply say we are converting time domain to frequency domain. Okay, let's go into little deep. A method to collect an NMR spectrum in which a pulse of radio frequency energy is used to excite all nuclei of a particular isotope, which may be H1 or C13, in the molecule simultaneously. So we are going to bombard all the frequencies simultaneously, so that all different protons in different environment, they absorb that energy, go to the higher state, and after they go to higher state, and when they fall back to their original state, they are going to re-emit the photon. Okay, as the excited nuclei relax, they re-emit the radio wave photons, which produce an interference pattern called the free induction decay. So this is called as FID, free induction decay. So just recollect what we have done. There are all type of sets of protons there. We bombarded that different set of protons with radio waves. Because all of them have different energy, they will absorb different energy, and when they fall back to the ground state, they will emit photons of different energy. So all the photons together will give you FID, free induction decay. A mathematical process called Fourier transform is used to convert FID into NMR spectrum. So this is how FID looks like. When Fourier transform mathematical process applied to it, you get a proper NMR signal, where on x-axis you have ppm delta. A mathematical process called Fourier transform is used to convert FID into NMR spectrum. Here it is time domain, and here it is frequency domain. So this is the flow chart. You may write it in your exam also. Stimulate all transitions simultaneously. In other words, you are going to excite all the protons simultaneously. The spectral range is not scanned continuously, so you do not use monochromator. Simply bombard your molecule with all the energy simultaneously instead of one type of energy, that is one wavelength at a time. Each of frequency increment is exposed to a field of a very short time, that is 10 microseconds. Sample irradiated by a pulse of radio frequency radiation containing all the frequencies over the H1 range. That is, the field is fixed. External magnetic field strength is fixed. The relaxation by emitting the radiation, that happens when the nuclei falls back to the ground state, and it produces a signal which is nothing but your free decay FID, which is in time domain spectrum, and we saw how it looks like. FID signal contains the vector sum of the responses from all the spins. So basically what happens is, as the nuclei are coming to the ground state, they emit all sorts of wavelength depending on different sets of proton. So from one set of proton you will get only one wavelength, but all the protons together will give you combination of signals. So it is a vector sum of all individual signals. So Fourier transform converts that FID into frequency domain spectrum. So you can say that this is the conversion that you can see on your screen. FID is over here, and here it is in the frequency domain. Now this is important for you. They may ask specifically in examination conversion from time domain to frequency domain. The ordered FID is an interference signal between the radio frequency source, for example 300 megahertz, and a frequency emitted by the excited proton. See, there will be some radio source frequency also in there. Okay, this output is digitized in a computer, and individual frequencies due to different nuclei are extracted out from the interference pattern or interferogram, nothing but FID only. Okay, this is FID only by on a computer by a mathematical method called Fourier transform analysis. The Fourier transform separates FID into its sine or cosine wave components. So wavelength is given as lambda is equal to 1 upon frequency of the nucleus minus frequency of the pulse. So what you will get from I should say from the resolution is combination of wavelengths. So you can calculate this. So from this equation, the exact frequency can be found out as the known frequency. See, what we are interested as, we are interested in this frequency. FID will give you this. So this will be known because the computer will give you that value. Then you know what pulse you are inputting, what pulse you are using. Suppose you are using 300 megahertz pulse. So that frequency you will know. So if these two values are known, you can calculate frequency of the nucleus. So from above equation, the exact frequency can be found out. However, this exact value is not really required, as we shall be expressing the absorption frequencies, frequency of the pulse, absorption frequencies, frequency of the pulse is as chemical shift. Discussed, we will discuss that again in the next step. So the chemical shift is nothing but your delta value. So on scale of delta, it can be calculated as frequency of the nucleus minus frequency of the pulse divided by frequency of the pulse. So we are first calculating the nucleus frequency, then we are calculating the delta. Now in modern computers, all of it is done by computers. This is how it is done. This is the simplest graphical representation we can get. See, that green color is the resulting signal. So it is resolved like this, and these are the two frequencies that are underlying the signal. Just see that one more time. You may zoom into your screen, try to pinch in and pinch out on the screen, so you will be able to see it properly. There is another representation. हेलो मैडम. हाँ हाँ, गुड मॉर्निंग मैडम. हाँ, मैं लेक्चर में हूँ मैडम. मैं आपको 15-20 मिनट बाद फोन करूँगा. Okay, so this is frequency domain. Another representation, how if you go on adding the wavelength, go on adding the waves, what will be the resultant of it. So what are advantages of FT-NMR? See, it increases the sensitivity very high. So dramatic increase in the sensitivity of NMR measurement has widespread application, especially for C13 NMR, P31, that is phosphorus 31 NMR, F19 NMR, giving high signal to noise ratio, facilitating rapid scanning. Now the problem with C13, P31 and F19 NMR is their concentration is very low. Okay, their concentration is very low. So in the signal there is lot of noise if you go by conventional NMR. But when we use FT-NMR, you will very high sensitivity for those carbon, phosphorus and fluorine. Now signal can be obtained with less than 5 milligram of compound. The signal stand out clearly with almost no electronic background noises. It is used in engineering, industrial quality control and in medicine. See, MRI, magnetic resonance imaging, is a type of NMR only, FT-NMR only. That is the most important FT-NMR application. Now, if you